Right now, as you watch this video, every atom in your body is telling the story of the most extraordinary 3 minutes in cosmic history. The carbon in your muscles, the oxygen in your lungs, the calcium in your bones. None of it should exist. For decades, scientists believed these elements formed slowly in stellar cores over billions of years. We were completely wrong about when the universe's creative power peaked. The shocking truth is this: in just 180 seconds after the Big Bang, the universe accomplished something so precise, so perfectly calibrated that changing any variable by even 1 part in a billion would have meant you, me, and everything we know could never have existed. Those 3 minutes didn't just create atoms. They created the fundamental recipe that would determine whether galaxies could form, whether stars could ignite, whether planets could harbor life, and whether consciousness could emerge to contemplate its own existence. Consider this staggering reality. The universe at 180 seconds old was 1 billion degrees Celsius hotter than the core of the most massive stars. Yet in that infernal crucible, nuclear reactions were occurring with such mathematical precision that they laid the foundation for every structure we see today. The cosmic microwave background radiation we detect shows us the exact fingerprint of those 3 minutes, preserved across 13.8 billion years like a cosmic birth certificate. But here's what makes this discovery truly disturbing. The nuclear physics governing those first 3 minutes operates on tolerances so narrow that Stephen Hawking called it the most finely tuned process in the known universe. If the strong nuclear force had been 2% weaker, no carbon could form. If it were 2% stronger, all hydrogen would have fused into heavier elements, making stars impossible. The universe threaded a needle so precisely that Nobel laureate Steven Weinberg described it as almost miraculous. What we've discovered about those 3 minutes has shattered every assumption about cosmic timing, elemental abundance, and the very nature of why complexity can exist. Tonight, we read diving into the minute-minute account of how everything you see around you, from the lightest hydrogen to the heaviest gold, traces its origin to nuclear reactions that occurred when the universe was smaller than our solar system and younger than a human heartbeat. Through the revolutionary work of Ralph Alpher, Robert Herman, and George Gamow in 1948, and confirmed by NASA's COBE and WMAP satellites, we now possess a precise timeline of cosmic nucleosynthesis. We know exactly how temperature, density, and nuclear cross-sections combine to forge the elements. We can calculate the abundance ratios with extraordinary accuracy. Most remarkably, we can prove that this 3-minute window was the only chance the universe would ever have to create the perfect blend of hydrogen and helium that makes galaxies possible. The implications stretch far beyond physics. These discoveries revealed that the universe's capacity for complexity, beauty, and consciousness was determined in the time it takes to brew a cup of coffee. Every symphony ever written, every sunset ever admired, every thought ever contemplated depends on nuclear reactions that occurred when space itself was still glowing white-hot from creation's birth. As we journey through this cosmic timeline, you will all discover why modern cosmologists call those first 3 minutes the universe's finest hour. Not because they were the most dramatic, but because they required the most exquisite precision. You will understand why Carl Sagan wrote that "We are made of star stuff" was only half the story. The complete truth is far more extraordinary. We are made of universe stuff, forged in the very first furnace that ever burned. If you are fascinated by how the deepest mysteries of existence connect to the most fundamental moments of cosmic history, subscribe and hit thumbs up. And here is a question that will blow your mind by the end of this video. What if I told you that the ratio of protons to neutrons during those 3 minutes was so precise that shifting it by 0.1% would have made the universe permanently sterile? Comment below with your thoughts on how such precision can emerge from apparent chaos. The journey we're about to take spans from quantum mechanics to cosmic architecture, from nuclear physics to the meaning of existence itself. We'll witness how the universe's temperature dropped from 10 billion degrees to 1 billion degrees, how neutrons raced against radioactive decay, and how the cosmic expansion rate had to hit a Goldilocks zone that lasted exactly as long as nuclear fusion needed to work its magic. But perhaps most profoundly, we'll explore how those 3 minutes reveal something unexpected about the nature of time, causality, and the deep structure of reality. The precision required wasn't just mathematical. It suggests something far more mysterious about why the universe seems fine-tuned for complexity, consciousness, and wonder. Now let's begin our journey into the most consequential 3 minutes in cosmic history. Chapter 1. Cosmic Foundation. The story of everything begins not with light, but with an explosion so violent that space itself had to expand faster than the laws of physics normally allow. At precisely Y-43 seconds after the Big Bang, a moment cosmologists call Planck time, the universe was smaller than a subatomic particle and hotter than any temperature we can meaningfully describe. But by the time our 3-minute story begins, at roughly 20 seconds after creation, something remarkable had already occurred. The universe had become cool enough for nuclear physics to take control of cosmic evolution. Picture this. At 20 seconds old, the universe was still 100 times hotter than the sun's core, with temperatures reaching 3 billion degrees Celsius. Yet this represented a dramatic cooling from the incomprehensible heat of the first moments. Space was filled with a primordial soup of protons, neutrons, electrons, and photons, all colliding with such ferocious energy that no atomic nuclei could survive for more than microseconds before being blasted apart again. The critical insight that changed our understanding came from Ralph Alpher and Robert Herman's 1948 calculations, later refined by Fred Hoyle and others. They realized that the early universe's conditions created a narrow window where nuclear fusion could occur without the immense gravitational pressures needed to ignite fusion in stellar cores. The universe itself had become a cosmic reactor, with temperature and density perfectly calibrated for nucleosynthesis. But here is the first crucial revelation. The universe was expanding so rapidly that this nuclear window would slam shut within minutes. While the temperature remained high enough for fusion, the density was plummeting exponentially. George Gamow calculated that the universe had perhaps 180 seconds, 3 minutes, before expansion would cool and thin the cosmic soup below the threshold needed for nuclear reactions to continue. To understand why this timing was so critical, consider the nuclear physics involved. For 2 protons to fuse and create heavier elements, they must overcome the electromagnetic force that violently repels positively charged particles. In stars, this happens because gravity compresses matter to extraordinary densities while maintaining billion-degree temperatures for millions of years. But the early universe offered different conditions. Even higher temperatures, but densities that were dropping every second as space expanded. The expansion rate itself revealed the universe's most fundamental properties. Edwin Hubble's observations in the 1920s showed us that galaxies are racing away from each other, but cosmologists in the 1940s realized they could reverse engineer this expansion to determine exactly how dense and hot the universe had been at any previous moment. The mathematics were unforgiving. If the universe expanded too quickly, matter would thin out before nucleosynthesis could begin. Too slowly, and the universe would collapse back into a black hole before stars could form. What emerged from these calculations was a cosmic Goldilocks scenario that defied probability. The expansion rate had to be precise to within 1 part in 1015. Imagine trying to measure the distance from Earth to the Sun to within the width of a human hair. This precision wasn't optional. It was the difference between a universe capable of creating complexity and one condemned to eternal simplicity. During these first crucial seconds, the universe contained roughly equal numbers of protons and neutrons, the building blocks that would soon become atomic nuclei. But neutrons face a deadly problem. When free in space, they decay into protons, electrons, and neutrinos with a half-life of about 15 minutes. This meant the clock was ticking not just against cosmic expansion, but against radioactive decay that was steadily reducing the neutron supply needed for heavier elements. The temperature at 20 seconds, still 3 billion degrees, was just beginning to drop below the threshold where photons carry enough energy to instantly break apart any deuterium nuclei that might form. Deuterium, consisting of 1 proton and 1 neutron, would prove to be the crucial stepping stone to helium and the foundation of all nucleosynthesis. But for deuterium to survive long enough to participate in further reactions, the universe needed to cool just enough that photons couldn't destroy it faster than nuclear reactions could create it. NASA's COBE satellite in the 1990s, followed by the Wilkinson Microwave Anisotropy Probe, WMAP, gave us unprecedented precision in measuring the cosmic microwave background radiation, the afterglow of these first moments. The data confirmed that the universe's temperature, density, and composition during nucleosynthesis matched theoretical predictions with startling accuracy. We could literally see the fingerprint of 3-minute-old nuclear reactions, preserved in radiation that has traveled unimpeded for 13.8 billion years. Consider the extraordinary fact that we can reconstruct, second by second, the nuclear processes that occurred when the universe was younger than most commercial advertisements. We know that at exactly 100 seconds after the Big Bang, the temperature dropped to 1 billion degrees. Still, 60 times hotter than the sun's core, but cool enough for the first stable atomic nuclei to begin forming in significant quantities. The precision required for this cosmic nuclear reactor goes beyond mathematical elegance. It reveals something profound about the fundamental constants of physics. The strong nuclear force that holds atomic nuclei together, the electromagnetic force that governs how protons repel each other, the rate of cosmic expansion determined by dark energy and dark matter, all had to conspire with extraordinary precision to create conditions where complex nuclei could form during this brief window. As we stand at the threshold of minute 1, with the universe cooling rapidly and neutrons beginning to bind with protons in reactions that will determine the cosmic abundance of elements for all of cosmic history, we face our first profound realization. The next 180 seconds won't just create hydrogen and helium. They will establish whether stars can form, whether galaxies can coalesce, whether planets can develop, and ultimately whether the universe will remain forever simple or become capable of extraordinary complexity. The stage is set for nuclear reactions that will prove to be the most consequential chemistry experiment in cosmic history, one where the universe itself serves as both laboratory and subject, and where the precise calibration of fundamental forces will determine whether consciousness could ever emerge to contemplate its own existence. Chapter 2. Nuclear Awakening. At exactly 1 minute after the Big Bang, the universe reached a temperature of 1.4 billion degrees Celsius, still unimaginably hot, but cool enough for nuclear physics to begin its most important work. This moment marks what cosmologists call the deuterium bottleneck, the critical threshold where the first stable atomic nuclei could survive long enough to participate in further nuclear reactions. Everything that follows in cosmic evolution depends on what happened in the next 60 seconds. The deuterium nucleus, consisting of 1 proton bound to 1 neutron, is remarkably fragile compared to the nuclei that will follow. At temperatures above 1 billion degrees, high-energy photons carry enough punch to instantly blast deuterium apart faster than nuclear reactions can create it. But as the universe's temperature dropped below this threshold, something extraordinary began. For the first time since the Big Bang, atomic nuclei could form faster than radiation could destroy them. James Peebles at Princeton University And independently, Yakov Zeldovich in Moscow calculated that this transition would happen explosively fast. Once deuterium could survive, nuclear reactions would cascade rapidly through a series of fusion processes, creating helium-4 nuclei with unprecedented efficiency. The window would be brief, perhaps 120 seconds, but the nuclear furnace would burn with such intensity that it would forge roughly 25% of all protons into helium, establishing the cosmic abundance ratio that persists today. Here's where the physics becomes almost magical in its precision. For deuterium to form, a proton and neutron must collide with exactly the right energy to overcome electromagnetic repulsion while staying below the threshold that would blast them apart again. The cross-section for this reaction, essentially the target size that particles present to each other, is incredibly small. Yet in the dense, hot conditions of the 1-minute-old universe, these reactions were occurring trillions of times per second throughout every cubic centimeter of space. The neutron abundance at this moment was critical. Free neutrons decay with a 15-minute half-life, so by 1 minute after the Big Bang, roughly 15% of the original neutrons had already decayed into protons. The remaining neutron-to-proton ratio was approximately 1 to 7, a proportion that would directly determine how much helium the universe could manufacture. This wasn't random. It was determined by the precise balance between the weak nuclear force governing neutron decay and the expansion rate of space itself. NASA's Planck satellite measurements, released in 2013, confirmed this neutron abundance with extraordinary precision. The cosmic microwave background shows us that at nucleosynthesis, the universe contained exactly 0.022 neutrons for every proton, a ratio that matches theoretical predictions to better than 1% accuracy. This agreement represents one of the most precise confirmations of Big Bang cosmology and our understanding of fundamental physics. As deuterium nuclei began accumulating in significant quantities, they immediately became targets for further nuclear reactions. A deuterium nucleus could absorb another neutron to form tritium-heavy hydrogen. The pathway to helium-4 reveals the elegant choreography of nuclear physics operating under extreme conditions. Deuterium could fuse with tritium to create helium-4 plus a neutron, or two deuterium nuclei could combine to form either tritium plus a proton or helium-3 plus a neutron. Multiple reaction chains were operating simultaneously, all converging on the same endpoint, converting neutrons and protons into the most stable light nucleus nature allows. What makes this process so remarkable is its efficiency. While stellar nucleosynthesis in the cores of massive stars requires millions of years to fuse hydrogen into helium, the early universe accomplished the same nuclear transformation in less than 3 minutes. The key difference was temperature and density, conditions so extreme that nuclear barriers that normally require eons to overcome could be surmounted almost instantly. Robert Wagner's detailed calculations in the 1960s revealed that this nuclear cascade would continue until virtually every available neutron had been incorporated into helium-4 nuclei. The process was self-limiting. As neutrons were consumed, the nuclear reactions would slow and eventually halt, leaving the universe with a specific ratio of hydrogen to helium that would remain unchanged for billions of years. The implications extend far beyond nuclear physics. The helium abundance established during these first minutes would determine the evolution of the first generation of stars. Stars containing primordial helium burn differently than pure hydrogen stars. They're more massive, more luminous, and more capable of creating the heavy elements needed for rocky planets and biological complexity. Without the precise helium abundance forged during nucleosynthesis, stellar evolution would have followed a completely different path. Consider the extraordinary sensitivity of this process to fundamental constants. If the strong nuclear force were 2% weaker, deuterium would be too fragile to survive even at these lower temperatures. and nucleosynthesis would halt before producing significant helium. If the electromagnetic force were slightly different, the nuclear reaction rates would shift, dramatically altering the final abundance ratios. If the universe's expansion rate were faster or slower by even 1%, the temperature and density window for nucleosynthesis would shift, preventing the formation of heavy elements. The 2-minute mark represents the peak of nuclear activity. At this point, with temperatures around 900 million degrees, nuclear reaction rates reached their maximum efficiency. Helium-4 production was proceeding at maximum speed, limited only by the availability of neutrons and the ever-expanding universe's decreasing density. The cosmic nuclear reactor was operating at full throttle, but the fuel supply was already running low. By minute 2.5, something crucial was becoming apparent. The nuclear reactions were becoming neutron-starved. Nearly every available neutron had been bound into helium nuclei, but significant quantities of deuterium and helium-3 remained. These leftover nuclei would survive to the present day, providing crucial observational evidence for the Big Bang theory and precise measurements of the universe's conditions during nucleosynthesis. Fred Hoyle, initially a skeptic of Big Bang cosmology, performed calculations showing that the predicted abundance of deuterium in the early universe should be approximately 0.002% by mass, a prediction that seemed almost impossibly precise to test. Yet when astronomers began measuring deuterium in interstellar space and in the atmospheres of Jupiter and Saturn, they found abundances matching this theoretical prediction with startling accuracy. As we approach minute 3, the universe has fundamentally transformed. What began as a chaotic soup of individual protons and neutrons has become an organized collection of atomic nuclei, with hydrogen comprising about 75% of normal matter and helium making up nearly all of the remainder. This wasn't gradual stellar cooking over cosmic time. This was rapid, precise nuclear assembly occurring faster than most chemical reactions proceed on Earth. The universe was about to cross another crucial threshold. Temperatures would soon drop below the point where nuclear reactions could continue efficiently, but the nuclear abundance pattern established in these first minutes would remain frozen for all of cosmic history. The cosmic nuclear furnace was about to shut down, leaving behind the raw materials from which stars, galaxies, and ultimately life itself would eventually emerge. Chapter 3. Fusion's peak at 2.5 minutes after the Big Bang. The universe reached the crescendo of its nuclear symphony, with temperatures hovering at 800 million degrees Celsius, still 50 times hotter than the Sun's core. Nuclear fusion was proceeding at maximum efficiency. This represents the peak moment of cosmic nucleosynthesis, when the universe transformed from a collection of isolated protons and neutrons into an organized system of atomic nuclei that would define the chemistry of space for all future time. The nuclear reaction networks operating during this peak were extraordinarily complex. Unlike the relatively simple proton-proton chain that powers stars, the early universe supported multiple simultaneous fusion pathways. Deuterium nuclei were combining with protons to form helium-3, while simultaneously fusing with neutrons to create tritium. Tritium was rapidly decaying or fusing with deuterium to produce helium-4. Most efficiently, deuterium nuclei were combining directly with each other through several reaction channels, all leading toward the same endpoint: the creation of helium-4, the most tightly bound light nucleus in existence. Donald Clayton's groundbreaking work in nuclear astrophysics revealed why helium-4 became the dominant product of primordial nucleosynthesis. Its binding energy per nucleon, the energy required to break apart the nucleus, is significantly higher than any lighter nucleus. This means that once formed, helium-4 nuclei were extremely stable and unlikely to be destroyed by subsequent collisions. The universe was naturally selecting for the most stable nuclear configuration possible under these extreme conditions. But here is where the physics becomes truly remarkable. The production of elements heavier than helium-4 hit a seemingly insurmountable barrier. There are no stable nuclei with mass numbers 5 or 8, creating what nuclear physicists call the mass gap. Helium-4 nuclei couldn't simply absorb another proton or neutron to create a stable, heavier element. The next stable nucleus, lithium-6, required a much more improbable collision between helium-4 and deuterium, while lithium-7 needed an even rarer three-body collision. This mass gap explains one of the most profound features of our universe: why hydrogen and helium dominate cosmic abundance while heavier elements remain rare. The universe's first nuclear furnace could efficiently produce elements up to mass 4, but creating anything heavier required reaction pathways so improbable that only tiny traces of lithium and beryllium were formed. The heavy elements that make rocky planets and biological life possible would have to wait for stellar nucleosynthesis billions of years later. Fred Hoyle's calculations in the 1950s showed that this mass gap was actually essential for cosmic evolution. If the early universe had efficiently produced heavy elements, it would have created a completely different cosmic environment. Stars would have formed with high metallicity from the beginning, burning faster and dying sooner. The slow stellar evolution necessary to create stable planetary systems and allow time for biological development required a universe that began with simple hydrogen and helium. The neutron supply during this peak phase was becoming critically depleted. By 2.5 minutes, radioactive decay had reduced the neutron to proton ratio to approximately 1:7, and nuclear reactions were rapidly consuming the remaining neutrons. Each neutron that survived was precious. It determined whether the universe would produce the optimal amount of helium for future stellar evolution or fall short of the abundance needed for complex galactic chemistry. William Fowler is Nobel Prize-winning research on stellar nucleosynthesis helped establish why the helium abundance from this period was so crucial for later cosmic evolution. The first generation of stars, called population 3 stars, formed from primordial gas containing only hydrogen, helium, and trace amounts of lithium. The presence of helium changed their nuclear burning processes, making them more massive and enabling them to create the first heavy elements through stellar nucleosynthesis and supernova explosions. At precisely 150 seconds after the Big Bang, with temperatures at 700 million degrees, nuclear reaction rates began noticeably slowing. The universe's expansion had reduced matter density to the point where nuclear collisions became less frequent, while the dropping temperature made it increasingly difficult for nuclei to overcome electromagnetic barriers to fusion. The cosmic nuclear reactor was beginning to wind down, though it would continue operating at reduced efficiency for another minute. The precision required during this peak phase reveals something extraordinary about the fundamental structure of reality. The nuclear reaction cross-sections, the expansion rate of space, the neutron decay rate, and the electromagnetic fine structure constant all had to align within incredibly narrow tolerances. Change any of these parameters by even small amounts, and the universe would have produced either too little helium to enable complex stellar evolution or so much helium that hydrogen-burning stars couldn't form at all. NASA's measurements of the cosmic microwave background, combined with observations of primordial element abundances in the oldest stars and gas clouds, confirm that the universe achieved exactly the right balance. Helium comprises 24.7% of normal matter by mass, remarkably close to the 25% predicted by Bang nucleosynthesis theory. This agreement represents one of the strongest pieces of evidence supporting our understanding of cosmic evolution and fundamental physics. The efficiency of helium-4 production during this peak was extraordinary. Nearly every available neutron was being incorporated into helium nuclei, with the process limited only by neutron supply rather than reaction rates. In stellar cores, helium production is a slow, steady process requiring millions of years. But in the early universe, The combination of extreme temperature and density allowed nuclear fusion to proceed at maximum possible speed. Consider the scale of nuclear transformation occurring during these peak minutes. In every cubic meter of space, approximately 1,018 nuclear reactions were taking place every second. The universe was performing quintillions upon quintillions of nuclear experiments simultaneously, all following the same fundamental laws of physics, all converging on the same nuclear products. This represents the largest nuclear physics experiment ever conducted, with results we can still observe and measure today. The byproducts of this nuclear peak tell their own story. The deuterium that survived without being consumed in further reactions would become a cosmic fossil, preserving evidence of nucleosynthesis conditions. Its observed abundance in interstellar gas provides one of our most precise measurements of the universe's matter density during the first few minutes. Similarly, helium-3 and lithium-7 abundances serve as independent checks on our understanding of primordial nuclear physics. As the universe passed the 3-minute mark, nuclear fusion rates were dropping exponentially. Temperature had fallen to 500 million degrees, and matter density had decreased to the point where nuclear collisions became increasingly rare. The mass gap barrier to heavier element production became insurmountable, and neutron decay continued to reduce the fuel supply for any remaining nuclear reactions. The nuclear abundance pattern established during this peak would remain essentially unchanged for hundreds of millions of years, until the first stars began forming and stellar nucleosynthesis could resume the work of creating heavy elements. But those stellar furnaces would start with the raw materials forged in these first 3 minutes. A universe that was 75% hydrogen, 25% helium with trace amounts of deuterium, helium-3, and lithium serving as fossil evidence of the cosmos's nuclear origins. The universe had accomplished something unprecedented. It had created atomic nuclei more efficiently than any stellar core, established abundance ratios that would persist for billions of years, and laid the foundation for all subsequent cosmic chemistry. The peak of nuclear fusion was ending, but its products would enable everything that followed in cosmic evolution. Chapter 4: Helium's Triumph. By 3 minutes after the Big Bang, the universe had completed one of the most remarkable nuclear engineering projects in cosmic history. The conversion of approximately 1 neutron out of every 7 nucleons into helium-4 nuclei. With temperatures now dropped to 500 million degrees Celsius, nuclear reaction rates had slowed dramatically, but the cosmic nuclear furnace had already accomplished its primary mission. The universe had created a helium abundance that would prove absolutely critical for every phase of cosmic evolution that followed. The helium-4 nucleus represents a masterpiece of nuclear engineering by the laws of physics themselves. Consisting of 2 protons and 2 neutrons bound together with extraordinary stability, helium-4 has a binding energy per nucleon that exceeds every lighter nucleus. This means that once formed during primordial nucleosynthesis, these helium nuclei were virtually indestructible under the conditions of the early universe. They would survive unchanged for billions of years, waiting to play crucial roles in stellar nuclear burning and galactic chemical evolution. Subramanian Chandrasekhar's theoretical work on stellar structure revealed why the 25% helium abundance created during these first minutes was so perfectly calibrated for cosmic evolution. Stars forming from primordial gas with this helium content would have dramatically different properties than pure hydrogen stars. The presence of helium increases stellar opacity, making stars more massive, more luminous, and capable of reaching higher core temperatures needed for heavy element synthesis. But the triumph of helium production reveals something even more profound about the universe's fine-tuning. The nuclear reaction pathways that efficiently produce helium-4 depend on a delicate balance between the strong nuclear force and electromagnetic repulsion. If the strong force were just 2% weaker, deuterium nuclei would be too fragile to survive long enough for helium synthesis. If it were 2% stronger, protons would bind so easily that virtually all hydrogen would have been converted to heavier elements, making long-lived hydrogen-burning stars impossible. The pathway to helium-4 dominance involved multiple nuclear reaction chains operating simultaneously. The most efficient route involved two deuterium nuclei fusing directly to create helium-4 plus gamma rays, releasing substantial nuclear binding energy that helped maintain the high temperatures necessary for continued fusion. Alternative pathways through tritium and helium-3 also contributed, but the deuterium-deuterium fusion channel proved most important for establishing the final abundance ratios. Edwin Salpeter's calculations in nuclear astrophysics demonstrated that the helium abundance established during primordial nucleosynthesis would remain essentially unchanged throughout most of cosmic history. Unlike hydrogen, which stars continuously convert into heavier elements, helium created during the first 3 minutes was too tightly bound to be easily destroyed in stellar cores. Most of this primordial helium survives today, serving as a direct fossil record of the universe's nuclear birth. The precision of helium-4 production during these minutes can be measured with extraordinary accuracy through observations of the cosmic microwave background radiation and primordial element abundances in the oldest astronomical objects. The Planck satellite's measurements show that helium comprises exactly 24.7% plus or minus 0.2% of normal matter by mass, remarkably close to the theoretical prediction of 24.9% from Big Bang nucleosynthesis calculations. What makes this helium triumph particularly remarkable is how it solved multiple cosmic engineering problems simultaneously. The 25% helium abundance provided enough nuclear fuel to power stellar evolution over cosmic timescales, while leaving sufficient hydrogen for long-term galactic chemical evolution. It created the optimal conditions for population 3-star formation, enabling these first-generation stars to become massive enough to produce heavy elements through stellar nucleosynthesis and supernova explosions. The nuclear physics governing helium-4 formation reveals deep insights about fundamental forces. The nuclear reaction cross-sections, essentially the probability that colliding nuclei will fuse, had to be large enough to enable efficient fusion during the brief nucleosynthesis window, but not so large that all hydrogen would be consumed before stellar evolution could begin. This balance depends on the precise value of the nuclear force strength and the electromagnetic fine structure constant. By the end of minute 3, virtually every available neutron had been incorporated into helium nuclei. The neutron-to-proton ratio had dropped to approximately 1:7 due to radioactive decay, and nearly all surviving neutrons were bound in stable helium-4 nuclei. This neutron starvation effectively ended primordial nucleosynthesis, leaving behind a universe with a nuclear abundance pattern that would persist for hundreds of millions of years. The temperature at 3 minutes to 500 million degrees represents a crucial threshold in cosmic evolution. While still unimaginably hot by terrestrial standards, this temperature was too low to support efficient nuclear fusion for creating heavier elements. The universe had passed through its only opportunity to manufacture elements heavier than hydrogen in large quantities until stellar cores could reach even higher temperatures billions of years later. Roger Taylor and David Schramm's detailed studies of primordial nucleosynthesis showed that the helium abundance was remarkably insensitive to small changes in initial conditions, but extremely sensitive to the fundamental constants of physics. This robustness in production, combined with sensitivity to physical laws, makes helium abundance one of our most powerful tests of cosmological models and our understanding of particle physics in extreme environments. The helium nuclei created during this period carried with them a precisely calibrated amount of nuclear binding energy. When these nuclei eventually participated in stellar fusion reactions billions of years later, they would release this energy in controlled stellar cores, powering galactic evolution and enabling the formation of heavy elements essential for planetary systems and biological complexity. Consider the extraordinary fact that every helium nucleus in your body, whether in your blood, bones, or breath, was forged during these first 3 minutes of cosmic history. Unlike the carbon, oxygen, and other heavy elements that were created in stellar cores and scattered by supernova explosions, primordial helium has remained essentially unchanged since nucleosynthesis ended. These nuclei are direct samples of 3-minute-old matter, preserved across 13.8 billion years of cosmic evolution. The implications of helium's triumph extend beyond nuclear physics to the very possibility of cosmic complexity. Without the precise helium abundance established during primordial nucleosynthesis, stellar evolution would have proceeded very differently. Stars would have been either too short-lived to allow biological evolution or too cool to create heavy elements. The universe would have remained permanently simple, filled with hydrogen clouds, but lacking the chemical diversity needed for planets, life, and consciousness. The cosmic microwave background radiation carries the imprint of this helium abundance in its precise temperature fluctuations and polarization patterns. When we observe this ancient light with modern telescopes, we are seeing direct evidence of nuclear reactions that occurred when the universe was younger than most television commercials. The statistical mechanics of helium formation during nucleosynthesis left permanent signatures in the radiation that has traveled unimpeded for billions of years. As nucleosynthesis concluded at 3 minutes and 10 seconds after the Big Bang, the universe had achieved something unprecedented in its brief history. It had created organized atomic nuclei with precisely the right abundances to enable all future cosmic evolution. The triumph of helium production wasn't just a nuclear physics success. It was the foundation for everything complex and beautiful that would emerge from cosmic history in the billions of years to follow. Chapter 5. Elemental Ratios. The universe at 3.5 minutes old had achieved something that would seem almost miraculous if we didn't understand the precise nuclear physics involved. It had created exactly the right ratio of hydrogen to helium to enable cosmic evolution toward complexity. The final abundance pattern emerging from primordial nucleosynthesis, minus 75% hydrogen, 25% helium by mass, represents one of the most precisely calibrated outcomes in all of physics. With tolerances so narrow that changing fundamental constants by even tiny amounts would have made galaxies, stars, and life impossible. This elemental ratio wasn't arbitrary or accidental. It emerged from the intricate interplay between nuclear reaction rates, radioactive decay, cosmic expansion, and the fundamental forces governing atomic nuclei. Ralph Alpher and George Gamow's pioneering calculations in 1948 first revealed that Big Bang nucleosynthesis would naturally produce this specific abundance pattern, making testable predictions about cosmic chemistry that wouldn't be confirmed observationally until decades later. The 3-to-1 mass ratio of hydrogen to helium determines virtually every aspect of stellar evolution and galactic chemistry. Hydrogen provides the primary fuel for stellar nuclear burning, enabling stars to shine steadily for billions of years while slowly converting their hydrogen content into heavier elements. Helium serves as the secondary fuel that powers more advanced stellar evolution phases, allowing massive stars to reach the extreme temperatures needed to forge elements like carbon, oxygen, and iron through stellar nucleosynthesis. But here's what makes this ratio so remarkably fine-tuned. It sits precisely at the intersection of multiple nuclear physics constraints. If the universe had produced less helium, say 20% instead of 25%, the first generation of stars would have been unable to reach high enough core temperatures for heavy element synthesis. These population 3 stars required helium burning to achieve the extreme conditions necessary for creating carbon through the triple alpha process, where 3 helium-4 nuclei combine to form carbon-12. Conversely, If primordial nucleosynthesis had produced more helium, perhaps 30% or 35%, stellar evolution would have proceeded too rapidly. Stars with higher helium content burn hotter and faster, exhausting their nuclear fuel before planetary systems could form and evolve. The universe would have experienced a brief burst of massive star formation followed by rapid stellar death, leaving behind a galaxy filled with stellar remnants but lacking the long-term stability needed for biological evolution. The precision of this elemental ratio reflects the extraordinary fine-tuning of fundamental physics, constants during nucleosynthesis. Stephen Weinberg's calculations showed that the nuclear reaction rates producing this abundance pattern depend on the strong nuclear force strength, the electromagnetic force constant, the neutron-proton mass difference, and the cosmic expansion rate in ways that create incredibly narrow windows for success. Consider the role of neutron decay in establishing these ratios. Free neutrons decay into protons with a precise half-life of 14 minutes and 38 seconds, determined by the weak nuclear force. During the first 3 minutes, this decay process steadily reduced the neutron supply available for helium synthesis. If neutron decay were faster, fewer neutrons would survive to form helium. If it was slower, more neutrons would be available, potentially converting too much hydrogen into heavier elements. The cosmic expansion rate provided another crucial constraint. As space expanded, matter density decreased exponentially, reducing the probability of nuclear collisions needed for fusion reactions. The expansion had to proceed fast enough to prevent the universe from collapsing under its own gravity, but slowly enough to maintain fusion-supporting densities for the few minutes required to establish optimal abundance ratios. David Schramm and Gary Steigman's detailed analysis revealed that the observed abundance ratios provide one of the most stringent tests of cosmological models. The agreement between theoretical predictions and observational measurements of primordial element abundances constrains the number of neutrino species, the matter density of the universe, and the nature of dark matter with extraordinary precision. The trace elements produced during nucleosynthesis also tell crucial parts of this story. Deuterium abundance, measured at about 0.002% by mass, provides an independent measurement of cosmic matter density during nucleosynthesis. The amount of deuterium that survived without being consumed in further nuclear reactions depends sensitively on the balance between reaction, RATES, and cosmic expansion, offering a fossil record of 3-minute-old cosmic conditions. Lithium-7, produced in minute quantities during primordial nucleosynthesis, creates what cosmologists call the lithium problem. Theoretical calculations predict slightly higher lithium abundances than observations detect in the oldest stars, suggesting either unknown nuclear physics in the early universe or stellar processing that has depleted primordial lithium. This discrepancy highlights how precisely we can now model and test nucleosynthesis physics. The elemental ratios established during these first minutes remained essentially frozen for hundreds of millions of years, until the first stars began forming and stellar nucleosynthesis could begin creating heavier elements. But even today, after billions of years of stellar evolution, the universe's overall composition still reflects the primordial abundance pattern, roughly 70% hydrogen and 28% helium by mass in normal matter, with heavier elements comprising less than 2% of the total. This cosmic chemical composition enables the existence of both long-lived main sequence stars and the galactic chemical evolution necessary for planetary formation. Hydrogen burning provides stable energy output over billion-year timescales, while helium burning in evolved stars creates the carbon, oxygen, silicon, and iron needed for rocky planets. The precise balance allows both processes to operate efficiently across cosmic time. Modern observations confirm these abundance ratios with remarkable precision. The Wilkinson Microwave Anisotropy Probe, WMAP, and Planck satellite measurements of cosmic microwave background anisotropies provide independent confirmation of primordial element abundances. Spectroscopic observations of metal-poor halo stars reveal helium abundances consistent with Big Bang nucleosynthesis predictions. Deuterium measurements in quasar absorption line systems trace primordial abundances across cosmic history. The implications extend beyond astrophysics to fundamental physics. The success of Big Bang nucleosynthesis predictions represents one of the strongest confirmations of our understanding of nuclear physics, particle physics, and general relativity operating under extreme conditions. The precise agreement between theory and observation validates our models of the early universe and our understanding of how fundamental forces behave at energy scales far beyond terrestrial laboratory capabilities. Perhaps most profoundly, these elemental ratios reveal that the universe's capacity for complexity was established during its first few minutes. The nuclear abundance pattern created during primordial nucleosynthesis provided exactly the right raw materials for stellar evolution, galactic chemical enrichment, planet formation, and ultimately the biochemistry of life. This wasn't gradual fine-tuning over cosmic time. It was precise calibration achieved in less time than it takes to brush your teeth. The mathematical probability of achieving these optimal ratios through random chance appears vanishingly small. The nuclear reaction network's fundamental force strengths and cosmic expansion rate had to align with extraordinary precision to produce abundance patterns compatible with complex cosmic evolution. Whether this fine-tuning reflects unknown physics, multiple universes, or deep principles about the nature of reality remains one of the most profound questions in modern cosmology. As we'll discover, these perfectly calibrated elemental ratios would soon enable the formation of the first stars, beginning a new chapter in cosmic evolution where stellar nucleosynthesis could create the heavy elements needed for planets, chemistry, and life. But that stellar story was only possible because the first 3 minutes had provided exactly the right nuclear foundation upon which all subsequent complexity could build. Chapter 6: Nuclear Legacy. The nuclear reactions that concluded during the universe's first 3 minutes left behind more than just hydrogen and helium. They established a cosmic inheritance that would determine every aspect of cosmic evolution for billions of years to follow. The abundance pattern forged during primordial nucleosynthesis provided exactly the nuclear raw materials needed for stellar formation, galactic chemical evolution, and ultimately, the emergence of planetary systems capable of supporting complex chemistry and life. This nuclear legacy operates on multiple timescales simultaneously. On cosmic scales, the hydrogen-helium ratio established during nucleosynthesis would fuel stellar evolution for tens of billions of years, providing the nuclear energy source for galaxies across the observable universe. On stellar scales, the presence of primordial helium would enable advanced nuclear burning phases that create heavy elements. On planetary scales, the trace isotopes produced during nucleosynthesis would serve as cosmic fossils, preserving evidence of the universe's nuclear birth for modern astronomers to discover and measure. Fred Hoyle's revolutionary insight in the 1950s revealed why the nuclear legacy of the first 3 minutes was so crucial for cosmic evolution. The universe had created what he termed a nuclear enabling environment. Not just the right elements, but the right proportions to enable stellar nucleosynthesis, to bridge the mass gap that primordial processes couldn't cross. Stellar cores could use the helium created during the Big Bang to forge carbon through the triple Alpher process, beginning the stellar nucleosynthesis chain that would eventually create every element heavier than lithium. The precision of this nuclear inheritance becomes clear when we consider alternative scenarios. If primordial nucleosynthesis had produced a universe with 90% hydrogen and 10% helium, stellar evolution would have proceeded very differently. The first generation of stars, Population 3 stars would have been unable to reach the core temperatures necessary for heavy element synthesis. Without helium burning to power stellar evolution beyond hydrogen exhaustion, these stars would have died as white dwarfs, leaving the universe permanently enriched only in hydrogen and helium. Conversely, if the early universe had converted 40% or 50% of its mass into helium, stellar lifetimes would have been dramatically shortened. High helium stars burn hotter and faster, consuming their nuclear fuel in millions rather than billions of years. Such a universe would have experienced rapid stellar evolution but lacked the time, stability necessary for planetary formation and biological development. Complex chemistry requires not just heavy elements, but stars that live long enough for planetary systems to evolve. The isotopic legacy of primordial nucleosynthesis provides some of our most precise windows into early universe physics. The deuterium, comprising about 0.002% of cosmic hydrogen, serves as an exquisitely sensitive barometer of cosmic matter density during nucleosynthesis. Unlike other nuclear products, deuterium is easily destroyed in stellar cores, but extremely difficult to create through any post-Big Bang process. Every deuterium nucleus we observe today is a direct remnant of 3-minute-old nuclear reactions. Craig Hogan and others have used deuterium abundance measurements to constrain the cosmic baryon density, the amount of normal matter in the universe, with extraordinary precision. The observed deuterium abundance implies that normal matter comprises exactly 4.9% of the universe's total mass energy, with the remainder consisting of dark matter and dark energy. This represents one of the most precise cosmological measurements possible, derived entirely from nuclear physics operating during the universe's first few minutes. Helium-3, another nucleosynthesis remnant, tells a different part of the story. This rare isotope, comprising about 0.00% of cosmic helium, provides an independent check on nucleosynthesis models and cosmic expansion rates. Its observed abundance matches theoretical predictions with remarkable precision, confirming our understanding of nuclear reaction networks operating under extreme early universe conditions. The nuclear legacy also includes the absence of significant quantities of elements heavier than lithium. The mass gaps at atomic masses 5 and 8 prevented primordial nucleosynthesis from efficiently producing carbon, oxygen, or heavier elements. This apparent limitation was actually essential for cosmic evolution. It ensured that heavy element production would occur slowly in stellar cores over cosmic time, rather than all at once during the universe's first minutes. This gradual stellar enrichment process, enabled by the nuclear legacy of primordial nucleosynthesis, created the conditions necessary for complex cosmic chemistry. The first generation of stars formed from primordial hydrogen and helium lived out their nuclear burning phases and died in supernova explosions that scattered newly created heavy elements into the interstellar medium. Subsequent generations of stars formed from gas progressively enriched in carbon, oxygen, silicon, and iron, elements essential for rocky planet formation.